All right, ladies and gentlemen, now we are going to be doing U-substitution in a definite integral form. So the first method is called back substitution. So it's pretty much like our regular indefinite U-substitution, except we're going to kind of apply those limits of integration at the very end. So like a indefinite U-substitution, I'm going to identify what my U is. So I always like to look, what is inside of my parentheses. So my U pretty obviously here is x squared plus 1. And then our du is 2x dx. Now if I notice I have an x dx outside of the parentheses. So I can get x dx if I divide by 2. So I get x dx. Now if I'm setting up a U-substitution integral, I kind of like to put the parentheses first. And then I put the x dx stuff. And then I can kind of see, okay, x squared plus 1. What's inside of a parentheses here is u. And then the x dx is the 1/2 du. And I'm just going to put that 1/2 outside. And I'm going to perform the antiderivative. Now remember, when we're performing the antiderivative, we're technically adding a plus c in there. But when we're kind of evaluating limits of integration, that plus c kind of goes away, because you have the 1 stuff that you plug in, and then you minus the 0 stuff that you plug in, so you get a plus c, then you're subtracting the plus c, and it kind of goes away. So we kind of don't need to worry about that too much. So when I'm evaluating this, so I get the 1/2 times 1/4, so that's an 1/8 times u to the 4th. So we put, and it's called back substitution because we put back in that expression for u. So that's 1/8 times x squared plus 1 to the 4th. And then now, and we're evaluating it from 0 to 1. And now we just plug in the 1 into 0. So I get 1/8 times 1 squared plus 1 to the 4th minus the 1/8 times 0 squared plus 1 to the 4th. And at this point, you could just go to your calculator. If you got to this point, you did all the calculus right. It's just a matter of crunching the numbers in. But if I'm kind of like evaluating these individually, I get, 1/8 2 to the 4th minus 1/8 times 1 to the 4th. So this is going to be 16 over 8, which is 2 minus 1/8. So that's going to be 15 over 8. So the drawback of this sort of method here is after you do the U and you integrate, then you have to worry about plugging X back in, and then you're going to plug in the numbers, and you get complicated, order of operation expressions when you want to get those numerical answers. But the next method is a good method that kind of does the investing of thinking about the limits of integration at the beginning and creating an entirely new U integral. And it's actually, I would say, a preferred method because it takes a lot of that ugly parentheses stuff out. So what you're still going to do is you're going to identify your U. Any U substitution, you're going to identify your U out right at the beginning. So I'm still going to have U equals to x squared plus 1. But now, I'm actually going to be thinking about my new limits of integration. So my use of 1 is 1 squared plus 1, which is 2. And my use of 0 is going to be 0 squared plus 1, which is going to be 1. And now I'm going to do my du like I did before. And then I still want to get x dx by itself. So what we did here is we kind of did our scratch work. And we're going to rewrite our integral. I got the integral of 0 to 1 of x squared plus 1 cubed. And we're going to sit back and enjoy the ride and replace our limits of integration. So, because I plugged in 1 into my u expression, that's going to be 2. And 0 plugged into my u expression is going to give me 1. And I'm going to write that integral as u cubed times 1/2 du. And the good news here is I can just integrate this. That's a 1/4. And know that there's a plus c there, but those plus c's, cancel out. And we're evaluating this from 2 to 1. So I'm going to get 1/8 u to the 4th from 2 to 1. And I'm just going to plug in the 2. And I'm going to plug in the 1. So I get 16/8, which is 2 minus an 1/8. And that gets me the same 15/8. So what's nice about option 2 is you don't have to worry about going back and plugging in your x's and getting those really complicated expressions where you have to do a lot of order of operations. So why not just kind of put those limits of integration in terms of u also and just turn it into a much easier definite u integral where you can immediately evaluate the limits.